Today we go to the new chapter, which is about electron-phonon coupling. And last time we finished the chapter on the phonons, in particular the H3 enharmonic cubic terms that will lead to the phonon-phonon interaction and lead to the thermal equilibrium, thermal expansion, and so on. But we know that in the realistic solid-state materials, we have electrons and ions, and the phonons are due to the lattice vibrations, but those ions are coupled to the electrons through electron-ion potential, okay, which we introduced very early. And as you can see here, that at zero temperature, those ions are sitting still on the lattice sides and without any lattice vibration. But at finite temperature, so some atoms, in fact all ions, should vibrate. So based on this harmonic potential, and as a result, you can see that from this cartoon picture that in particular for a particular site, say site L, so the at zero temperature position is here, but at finite temperature, this ion at site L may shift to the nearby position by only a small amount, say YL, because of the lattice vibration. So now the new updated position for this ion on site L is moved to L prime. But if you look at the electron-ion potential, which is again attraction, the Coulomb attraction, so suppose there's an electron up here at site Ri, and before the ion shifts, so electron-ion, say vector, which will lead to the electron-ion coupling or electron-ion potential, should follow this vector, right? So Ri minus L. But once the ion gets shifts to the nearby position, so the vector also shifts. So vector connect this electron ion also gets shifts, and it shifts to a slightly different vector, which is Ri minus L minus YL, where YL is the displacement vector. So you could very clearly see that electron and ion somehow coupled, and as the ion moves, electron-ion potential also gets some shifts, or at least some subtle change may occur here. And we know that when ions vibrate, it leads to the phonon modes, and therefore effectively we can imagine that electron will couple to phonon because the lattice vibration, which lead to the displacement of the ion position, and the ion actually coupled to the electron through the electron-ion potential, and as a result, electron-ion potential also got shifts, and therefore electron coupled to phonon. So today, and also the coming lecture hours, we will derive such an electron-phonon coupling Hamiltonian. So this is just a cartoon picture, and you can imagine that everybody gets shift, and electron actually see the ions at slightly different positions at any finite temperature. As a result, all the electrons couple to all the ion in a slightly different way, and we could actually write down the approximated Hamiltonian to model such a tiny shift in ion position which coupled to the electrons. So the simple model that we start with is the assumption that approximation that the ion-electron interactions are all short-ranged, meaning they're both Coulomb screened, and we don't have to care about the this long-range Coulomb interactions between electron and ions, and we can simply just look at this short distance limit of this electron-ion potential. And second assumption is that the electrons here are taken independent fermions. Okay, so we ignored the electron-electron Coulomb interactions in Hamiltonian. Of course, they are present in the realistic solid-state material, but we could forget about this at this point. There's no problem that we ignored such a Coulomb interacting electron-electron coupling. So on a simple Brav's lattice, we can write down such a simple Hamiltonian to describe such an independent electron, independent phonon system. And we know very well that this, the first term describes the free electron gas without electron-Coulomb interactions, and the second term describes this free phonon. Okay, it's the second quantized form of the free phonon, and there's no talking between electron and phonon up to now. But we know that electron will couple to phonon somehow through the electron-ion interaction, so let's just examine this electron-ion potential more closely. So we can imagine that this, the total electron-ion potential is the sum of all such individual electron-ion potential. Okay, you sum over all the lattice sites and the sum over all individual electrons and this potential for each individual electron-ion potential sum, you got a total electron-ion potential. But if you look at the single electron-ion potential indicated here, and we could derive effective Hamiltonian where the electron coupled to phonon. So you can Fourier transform this kind of a single electron operator in this assumption here, saying that the the single electron operator here we modeled here is based on the assumption that this electron-ion potential will only lead to the change of the momentum of electrons, but not the ion. Okay, because ion is actually very heavy, much heavier object than electron. So when the electron interact with the ions, the ion is still there without much change with its momentum and position, but electron gets very much deflected by the scattering of the ion. And therefore, this electron-ion potential, we could simplify this V electron-ion by the assumption that only the electron density operator involved in such scattering. So this is something that we have encountered before, because remember, previously we discussed this kind of delta potential, right, for the single electron scattering, which means that the electron can actually hit this delta-like potential and then get, say, deflected away, and these processes involve only electron incoming and outgoing electron momentum k prime, and that's it. Okay, so likewise we could actually model or simplify such an electron-ion potential in Fourier space, in momentum space, following this single electron operator, which means that this scattering process involve only a single electron operator, because the ion is too heavy. Okay, so it will not get modified. Of course, the ion gets slightly modified. Okay, but we can neglect such a small change in the ion position, momentum, and so on. Okay, so then we can take the Fourier transform of this, the single electron operator. Imagine that we have a single electron coming in, carrying momentum k, and get scattered out with momentum k prime, and by this ion. When we perform such a Fourier transformation, so this is precisely this Fourier component of such a single electron, like a free electron wave propagating and hit the target and get reflected, and this is the Fourier component of such a single electron processes. So under such a simplified model, we could discuss, what if this, this ion position got changed, shifts from L, say, to L prime by a tiny amount of a displacement vector YL. So if this L gets shifted to L prime, then this potential also gets shifted. And let's just examine what the consequence of such a tiny shift in this ion position when we talk about this electron-ion potential. So let me just repeat this part of electron ion potential one more time. Before we consider the shifts of the ion position, and after we consider the shifts of the ion, so now the potential between electron ion has this form. Of course, in the single electron operator form of the electron ion potential, we should multiply the density operator of the electron, right? And just like what we have done before for the single electron, say, scattering event, and the operator form of such a single electron operator carries such an electron density operator, right? Remember that. And this potential term is simply just a function of the relative position between electron and ion. And this is the second quantized form of the single electron operator. So likewise, we should also multiply this electron density operator after we consider the shifts of the ion position. And we know very well that this is simply just, say, psi dagger of Ri, psi of Ri. So if you Fourier transform this psi dagger of psi, and you precisely get this form, right? C dagger k and ck prime, as we discussed before. So let's just talk about the change of this new electron ion potential in the second quantized form. So we call this H1. So the H1 is this. So let's just Fourier transform this H1. And we expect that still get the same form like before, right? Because the only thing I did is just shift this ion position by a tiny amount, and which will not change, this functional form or operator content of such a H1 Hamiltonian. However, we can imagine that when we Fourier transform this potential function here, due to this tiny shift, this Fourier coefficient might get modified. And we will derive such a new Fourier coefficient in just a moment. But imagine such a change will lead to the different prefactor or matrix element VKK prime, which I call this VKK prime tutor. Okay, so this original electron ion potential in the second quantized form will lead to this VKK prime. But after the shift, this new electron ion potential in the second quantized form has exactly the same Fourier decomposition, except now this prefactor is slightly different. So we got a shift from this VKK prime to VKK prime tutor. Okay? So all the information regarding the electron-phonon coupling is hidden in this V tutor coefficient. So we will study this in more detail just a moment. Okay, so this is the simplest version of electron-phonon coupling. It's very intuitive physics because we can visualize this change of this vector connecting electron and ion once the ion got shifted to the nearby position due to the vibrations. Okay, so let's take a short break. When we come back, we will analyze again the relationship between VKK prime and V tutor KK prime. Okay, so they are different only by a tiny amount, but that tiny amount determines the electron-phonon coupling. Good, so let's take a short break. So you could check the corresponding sections and chapters in our references, such as Flansburgh or Kittel's second book, I believe, is really clear, right? Presented here. And you can even visualize the change of this Fourier decomposition just by looking at this shifts in this ion position. Yeah.
这个 case 里面 electron 它可以被视为是独立的 fermion， 它有其他潜力，比如说金属，比如说这个物质里面金属电子要够稀疏。
Well, we will later analyze this electron-phonon coupling in different materials, such as in the insulators or in metals. So the answer for your question is that this electron-phonon coupling exists in all materials, regardless whether this material is insulator, semiconductor, semi-metal, whatever. And this independent electron approximation here is just a simplification of the calculation. So you could still imagine that even an insulator, you can imagine that if I consider some lattice vibration of the valence band, for example, okay? So even this is an insulator, that the valence band is fully occupied and conduction band is fully empty. But at finite temperatures, of course, you can imagine that some electron will actually hop to the conduction band, right? So we are talking about finite temperature physics. So then there's no problem that we could still find some almost free electron in the conduction band. What about this Coulomb potential between electrons, right? So of course, they should come into play, and we will study the effect of the electron-phonon coupling to the electron-electron interactions. But here, since this physics is really generic, even when this very strong Coulomb interacting electron systems, you can still imagine that at the finite temperatures, there are some very active electrons that are almost independent, like particles, okay, in your conduction band. So there's no problem that the electrons live in the presence of a Coulomb interaction environment. Okay, so at the finite temperatures, these are maybe subleading effect. Okay, so there are always some almost free electrons available in your band. Okay, so that this physics is still there. So this approximation or simplification doesn't make our theory, say, specific. It's really general. It's just that we don't have to deal with such complications. So they survive. This effect survives in the presence of all these complications. Okay, so let's look at this comparison between VKK prime and the tutor. As I mentioned, you could redefine your coordinate. So remember, this is Ri minus L. So I could just redefine this vector so that I call this Ri minus L a different name called R. So this is initial, but after VKK prime theta got slightly shift. In particular, it should sum over L. All right, so if you wish, you could use this same notation. And this minus YL vector is the difference between this initial and final, this initial and final potential. So of course, we should multiply this by electron density operator, but we could do that later, right? Because both before and after the shifts being considered, this electron density operator is always there. So we simply just need to discuss the coefficient change. So let's just manipulate this Fourier transform. Let me just rewrite this in a slightly different form. So I insert an exponential factor, the extra exponential factor, and then I subtract such an exponential factor. Okay? So if you look at this exponential factor, and this is the exponential factor that I add here, and then I simply subtract the same, or divide the same exponential factor here, right? Because the exponents are minus here. Okay, and this is plus. So and this two exponential factor just get cancelled exactly. Okay, so but I intentionally add and divide the same exponential factor for the later purposes. Okay, because now you can very clearly see why I'm doing this, because I could simply redefine my vectors by a shift, right? So now I could simply just regard the shifted vectors r minus l minus yl appearing here and there. They are all the same. So I could just call this shifted vector a new name called r prime. So then I could just use this new shifted vector r prime to represent such a Fourier transform. But you can see that this form looks exactly the same as before, right? So this form is precisely VKK prime. Okay, because for a fixed position L, this form is actually identical or equivalent to V of r. So of course you say that this r is different from r minus l, but again you could shift this definition of vector by minus l, and then you simply just get some unimportant factor, like e to the I k prime minus k dotted l, okay, which is something we will discuss later. So this factor will not get anything proportional to electron-phonon coupling. So the thing that couple electron and phonon is this term right here. So you can see very clearly that apart from the previous term VKK prime, you got some extra exponential factor e to the I k prime minus k dotted yl. Okay, and remember that you should add this electron density operator everywhere. So which means that the C dagger C operator will couple to YL, and you know very well what is YL. YL, in our discussion on this free phonon or harmonic oscillator problem, is YL is the displacement vector, right? Okay, remember YL plus P or minus P from the phonon operator, right? Remember that from your quantum mechanics and from previous chapters on the free phonons. So if you form a linear combination of displacement vector or displacement operator, x and p, with the coefficient, proper coefficient a and ib, and so on, and you can define a phonon destruction operator b, and the Hermitian conjugate of that is b dagger. Remember that. So very clearly that the YL is somehow a linear combination of b and b dagger. Okay, so from here you can very clearly see the connection between electron and phonon by looking at this YL, because we can second quantize this YL as a linear combination of a b and b dagger. So now b and b dagger will couple to C dagger C, and that's precisely electron-phonon coupling. All right? Okay, so but let's just derive this in more precise way. So let's just compare these two forms, VKK prime and VKK prime tilde. This is the single electron potential, right? And this is after. So they differ by an extra exponential Fourier coefficient here. And so let's just analyze this extra term. Of course, we need to Taylor expand this exponential factor. So let's just make an approximation that this momentum transfer k is really, really tiny, and also the displacement vector YL, and which is consistent with our interest or focus here, because we are focusing on the low temperature, low momentum transfer, and low energy excitations. of our problem, right? And so this k prime minus k is actually a momentum transfer, which is the momentum difference between the incoming and outgoing electron states, which is assumed to be very, very small. And of course, the YL is a tiny displacement of the ions. So this is also small. So these two small quantities dot product with each other is actually very, very small, even smaller. As a result, let's just look at this factor e to the I q dot YL, and we could Taylor expand this, which is 1 plus the linear term. So remember, we could Fourier transform this displacement vector YL to the normal mode coordinate. In this, normal mode variables q with, another e to the I q dot L Fourier coefficient here. So now you could really rid of this Taylor expansion, and remember that this YQ is the normal mode coordinate, which will be the linear combinations of boson creation and destruction operator, and which will couple to the electron operator, which we will combine in just a moment. So, but what about this? The first exponential factor e to the I k prime minus k dot L, as I mentioned, this is simply a factor which is unrelated to the electron-phonon coupling and which is related to so-called the band structure or the block wave function of electron states. So let us just summarize this term. So meaning this factor gives us some periodic or the block properties of the band structure, and this is really electron-phonon coupling. And so let's just analyze these two terms individually. So the block piece of the Hamiltonian is this. Remember, we need to add the electron density operator here, right? So after including everything, and this is the shifted Hamiltonian for electron-phonon system, and this is the block piece of this H1 term. And this block piece of the H1 term doesn't depend on the displacement vector YL, but it depends on this reciprocal lattice vector G, which will be important here. So remember, sum over L, e to the I q dot L, you got two different results, either 1 or 0, depending on whether this momentum variable is equal to a reciprocal lattice vector or not. Okay, so we have taken advantage of such identity many, many times in the past. Remember that. So when we sum over this exponential factor on the lattice, and depending on whether this momentum of the underlying lattice is actually equal to the reciprocal lattice vector, if this is the case, then this vector is actually 1, otherwise 0. So you simply just sum over all such 0 and 1. So for each individual term, for fixed L, this factor is either 1 or 0, but if you sum over L, you get factor of n here, where n refers to the number of sites. And therefore, this block term is given by factor of n times the remaining sum, which means that this term is nothing but this kind of a term related to the reciprocal lattice vector. And we know that the electron states on this periodic potential satisfy this block theorem. Okay? And this reciprocal lattice vector plays an important role to actually support such a block theorem. So as a result, we call this term the block term, because this is a term which depends only on the band structure. Meaning, this depends only on the the reciprocal lattice vector G, but we know that for different materials, you get different G vectors, right? So it is the lattice-dependent vector, but it is independent of the electron-phonon coupling. Okay, so let's just summarize this electron-phonon coupling term. So I simply just, for simplicity, ignore the summation over spin, but you should understand that the spin summation is included here. E to the I, k prime minus k plus q dot L, and k prime minus k dotted yq prime. Right? So let's just look at this. Right, indeed. Okay, so let's take a short break. When we come back, we will continue deriving such an electron-phonon Hamiltonian. Okay, so let's continue. So as I mentioned, when we Taylor expand this exponential factor, which leads to electron-phonon coupling, we get two terms in the leading order expansion. The first term is 1. Another, the second term is linear in displacement vector. So this 1 in the first term actually leads to the block contributions, the H block term. And you should always remember that this vector gives you at least two terms. And the first term is 1 times the block term, which is the block term. The second term here, linear in proportional to YL, we should also multiply this vector by e to the I k prime minus k dotted L, right? So this is the common vector, but then you get another Fourier coefficient e to the I q dot L coming from this change of coordinates to the real space coordinates for displacement vector to the normal mode coordinate yq. So in the normal mode coordinate, we could very easily second quantize this normal mode vibration, and we can define this boson or phonon creation destruction operator just like what we did before. Okay, so the remaining part is really straightforward extension to what we discussed for phonon chapter, except now you can see that this B and B dagger coupled to this electron operator, density operator, C dagger K, C, K prime. So let me just change the variables from this normal mode displacement vector to the boson or phonon creation destruction operator like this. So you can see that all this complicated prefactor you don't need to care, but you could recognize very easily that this is indeed a phonon coupled to electron density, right? You recognize this electron density operator, and you recognize the phonon creation destruction operator, so they are coupled by this linear coupling between electron operator and the electron density operator and the phonon creation destruction operator. So you could clearly see that this electron density coupled to both the creating phonon and destroying the phonon. When we create a phonon, we actually emit a phonon. And when we annihilate the phonon, we absorb the phonon. So you get both emission and absorption processes by this electron-phonon coupling term. So we will use a diagram to illustrate this electron-phonon coupling in just a moment. So let me just define this electron-phonon matrix element, which is all these complicated, say, prefactors here. So of course, these are functions of, say, momentum transfer k minus k prime, and also phonon polarization vector S, and this ion mass, and this frequency of this lattice vibration, and h bar, and so on. So this is defined as electron-phonon matrix element. So we call this matrix element because it is indeed a matrix element which depends on the initial electron state k and the scattered electron state k prime. So it is the matrix element of this electron-phonon Hamiltonian sandwiched by this initial and final state electron. And indeed, this is the matrix element. So as you can see that this k minus k prime vector, which is the momentum transfer, which is proportional to this phonon momentum, started this phonon polarization, and we know that when that occurred, which implies that phonon polarization should be proportional to the momentum of phonon, which is precisely the longitudinal phonon that we defined earlier. Remember that. Therefore, only the longitudinal phonon will contribute to this electron-phonon coupling, meaning S is actually parallel to this momentum transfer, and no transverse contributions, meaning the S and Q should go along and they should not be perpendicular to each other. And so let's just take advantage of such a simplified notation by defining this electron-phonon matrix element. And in that simple notation, so the Hamiltonian is given by H0 plus H1. Remember, H0 consists of free electron part plus the free phonon part. And H1 is a simplified form of electron-phonon coupling. So Q is the momentum transfer between incoming and outgoing electrons, and also it is the phonon momentum. As we defined previous lectures, that this processes could be either a normal processes where Q is simply just K minus K prime, or the Unclub processes where this K and K prime and Q involves the reciprocal lattice vector G, okay, when we apply this momentum conservation. So we will discuss this later, but let's just draw some diagram. Okay, so you could very clearly see that by exchanging the electron momentum, between incoming and outgoing electron and the phonon, we could accomplish such a coupling. So there are two terms. One is B dagger coupled to C dagger C. Another is B, so which means that it involves creation or emission of the phonon or absorption of phonon. So these two processes are equally important and having the same weight. So let's just draw the diagram. And this is the phonon emission. So the incoming electron carrying momentum K prime and is destroyed at this interaction vortex point, and after the scattering by phonon, the electron carry momentum K created, and then you create another phonon carrying momentum minus Q. Okay, so this minus Q is here for the B dagger term, but it's plus Q for its B. So electrons scattered by this another electron-phonon coupling and then create a phonon here. So this is the phonon emission process. Of course, you could have the phonon absorption processes, meaning the electron can actually absorb the phonon, and then the phonon gets suppressed, and then the phonon disappears after the scattering. So then you get the single electron state afterwards. Okay, so this is the phonon absorption, which is the other term. Okay, so then we officially derive such an electron-phonon coupling in the second quantized form. Okay, so later we will argue that this electron-phonon matrix element and this form will lead to the attraction between two electrons, which is the reason why the ordinary metal becomes a superconductor when the temperature is lower enough. But we will discuss the consequence of this electron-phonon coupling both on the electron band structure and also on the phonon band. Okay, so this interaction couples the electron band and the phonon band. Of course, you could very clearly see that since B and B dagger couple to C dagger C, so this will modify both the dispersion of the electron and also the dispersion of phonon or phonon frequency, and this will lead to a very interesting phenomena called the Coulomb anomaly at the Fermi surface or nearby the Fermi momentum. So there is a sharp change in density of states of electron and phonon. And this change of a singular behavior of the electron density of states will lead to many different interesting phenomena. And even nowadays we recognize that this kind of a Coulomb anomaly is responsible for a certain charge density wave of a new material like topological insulator and so on. Okay, so this electron-phonon coupling has a profound effect on both electron and phonon band. And this phenomena and this consequence is real, meaning it has been observed experimentally. Okay, so this is the real effect. This is something what happened in the realistic solid-state materials, and we should discuss the consequence of this electron-phonon coupling in more details next. So now you can appreciate all the stage that we actually paved or prepared in the previous lectures, so that you have clear pictures of the second quantization for electron and fermions, and also for bosons. So now they couple together. So you can see that this term is the coupling between the boson and two fermions. Okay, so at the second order in perturbation theory, so we can imagine that the Bose factor and the Fermi function will appear. Right? So in nature, there are several different forms of this kind, electron-phonon coupling or boson-fermion coupling. Okay? And in the high-energy physics field, people call this kind of coupling Yukawa potential, okay, which describes certain interactions between boson and fermions in the nucleus. But this boson-fermion interaction and take this electron-phonon form is actually a very generic interaction in nature. So it exists in many different areas in physics. It may take a slightly different form, but more or less they have this general features that the electron density coupled to a phonon or boson creation destruction operator. Okay, so now we get a new type of interaction in nature, meaning fermion can couple to boson. So previously we thought that fermion and boson live in a different world, but welcome to the real world, that all the charged particles are coupled in solid state, so that electron coupled to ions, and the ion can make such phonon excitations. So of course the phonon will couple to electrons. And today we introduce this very interesting new form of interaction between particles, namely fermion density coupled to the bosonic creation destruction operator. We have still half an hour, so we could continue studying the consequence of this electron-phonon coupling on this phonon energy and also on electron energy. So let's take a short break. So by the way, you could probably see this kind of notes in a slightly different form in Flansburgh and in Kittel's second book. So you could see these derivations in a slightly different way, but more or less you get the same result. Of course, you should get the same result. So no more questions? It looks simple. Yeah.
看起来最后一个需要的被整理成一个方案，就是我是不是那是不是其他的波种跟electron也可以最后也可以整理这种形式？
Yeah, good question. So the most cases that I know that the electron coupled, the fermion coupled boson takes more or less this form. Of course, there's slightly different variations of this sort, because you can imagine that this boson could be sort of a real boson, meaning it could be simply just this form, B coupled to C dagger C. Here, the phonon, which couples the electron density, takes this B plus B dagger form, which makes the real boson, because here, B plus B dagger, so each of this B and B dagger is a complex field, right? So when you combine this B and B dagger, you got the real field. However, in different variations of the sort, you may have simply just one species of B or B dagger which coupled to the C dagger C. So this is different. This is different. Because if only a single boson creation destruction operator coupled to the C dagger C, you don't have such a form. Of course, it looks like they are the same, but in general, they are not the same because we may imagine that we have two different types of fermions. One is the more mobile conduction electron. Another is more localized, local moment electron. So in many heavy electron systems, like transition metal compound, so you may have d electrons or f orbital electrons. And d electrons are more mobile than the f orbitals. But in many so-called Kondo lattice compounds, this conduction electron band or d orbital taking the role of the C dagger here, and the f electron play the role of the f operator here, and both C and F or D and F electrons are both fermions. But they could somehow hybridize, and in some cases they could couple to a boson like this. So this case, so the second term is Hermitian conjugate of the first term. So you can imagine that this Hamiltonian, of course, is not the same as this Hamiltonian. Why? Because the first term is the same, but the second term is not the same. Okay, so B dagger, C dagger, F is not here. So in any way, we can imagine that this two electron operator, C dagger and C, could carry the same momentum or a different momentum, and could be coming from the same electron band, or could be the case where one electron is more mobile, another electron is more localized. And they could be on the same site, or they could be on different sites of the lattice. And the boson also, you could imagine, in general, can take different forms, such as B plus B dagger, or simply just single boson, B, coupled to the electron density. So in different contexts, we may have different form electron-phonon-like coupling, just as I mentioned. Okay? So of course, the mechanism is different, but the final mathematical form in the second quantized fields, representations, they are pretty much similar. But this may just slightly differ from one another, but that slight tiny difference make a huge differences regarding the consequence of that term. Because whether you get both absorption and emission of phonon, and whether you get the B dagger, C dagger, C, or whatever, right? So in one case you get this term, but in another case you don't get exactly the same term like this. They're similar, but the consequences of those different but similar terms are different. So in many cases they are called Yukawa term, but Yukawa term is not exactly the same as electron-phonon coupling right here, but just taking a very similar form. So good, but we could study those different electron-phonon-like term case by case, but then the consequence of this similar but different electron-phonon-like coupling will be different. Of course, something still very similar, that something is the fact that the electron density coupled to a phonon-like object. And so it involves both the Bose factor and the Fermi function. So in that regard, they're pretty much very similar, but the specific predictions are different, which makes our physics world very rich, because you cannot simply just use the same form. Of course, they are not the same form. They are not the same phenomena. So otherwise, we don't have such a rich phenomena here. But you could still see the different phenomena. They have the common theme. That common theme is that they are all coming from electron-phonon-like coupling or boson-fermion interactions. And this is the more generic features. So let's just calculate. But this is a good question. So if you are interested in more advanced solid-state materials or high-energy nuclear physics, and you will encounter such fermion-boson coupling a million times. And you will then recognize the differences between this seemingly similar electron-phonon-like coupling. So of course, the consequence of this electron-phonon coupling are twofold. One is to modify the phonon energy or phonon frequency, omega q. And of course, it will also change the electron energy dispersion, or electron band, meaning epsilon k. So let's just do some simple perturbation calculation. You can imagine that I have a ground state which is made of the free electron and free phonon, simply just H0. So you know very well what this ground state is for free electron and free phonon system. Now you couple the free electron and free phonon, and you consider this ground state, which is the main body ground state of H0, the state phi, as an unperturbed eigenstate. And then you do perturbation, and you put this electron-phonon Hamiltonian here, and to calculate this expression value of such a term, and at this first non-trivial order, which is a linear order in H electron-phonon, of course, you could have the second-order contributions. Following the standard second-order perturbation theory in quantum mechanics, and of course, you have higher-order contributions, which we neglect here. And the state phi, so let me just define it more clearly. It involves a number of longitudinal phonon modes. Remember, only longitudinal phonon will couple to electron. And also, it involves this free electron number operator, fill up the Fermi surface, and so on. And these two quantities could define this state phi, and we take the state phi as a non-perturbed eigenstate, and we perturbed around this phi by taking this H electron phonon as the small perturbation, and we do first order, second order perturbation. And so let's just look at the first order term, and you know very well that this epsilon 1, which is this part of a matrix element, vanishes. And of course, this will be your homework. For a long time you don't have homework assignment, but this finally is a very good exercise. So I mentioned this kind of vanishing of the first order corrections many times in the past. You should, of course, guess the reason why this matrix element, the first order term, vanishes, which is precisely because of orthogonal and normalization conditions of this non-perturbed eigenstate phi. And if you insert the linear term HEP, it involves changing the phonon number by 1, because you got only B and B dagger once, okay? And then once you apply this B and B dagger on both sides of this Dirac-Broglie cascade, you will change the phonon number by 1, plus or minus 1. And then when you sandwich this to states, you got different occupation number between the left and right states of Dirac state, and so you get orthogonal condition, and it becomes 0. But please explicitly prove that. I already told you the answer, but you need to convince yourself. Okay, so let's look at the second order. The second order term looks horrible, but we need to live with this just once in your lifetime. So this looks very similar to this Hartree-Fock expansion. Remember the Hartree-Fock? Okay, so we plug in the operator form of this HEP, and at the second order you get this complicated object. So in a number of operators, and you know that there are 3 operators here, initial state and another over there, final state. As before, the non-zero term arises when we have such a match between the initial and final momentum of electron and phonon. So let's just look at the final result. Suppose that this K triple prime is the same as K, and K double prime is the same as K prime, and this matrix element will match. And when you square this m, you get precisely this form. So when these two momentum match that two momentum, this matrix element here is actually the complex conjugate of that matrix element. So if you multiply these two conjugate factors, you get the absolute value square of that matrix element, right? And of course, the other cases, you get 0. We don't talk about that. So let's just look at this simplified form. Still horrible, but manageable right now. So you could use a diagram or diagrammatic or graph or so-called Feynman diagram to simplify this complicated 6-operator interaction. So let me just use a diagram to illustrate this two forms. So first, you annihilate the electron carrying state K, and you absorbed the phonon with momentum minus q at the same time, and then intermediate state is the electron state carrying momentum k prime, and after the scattering you get the phonon emission with minus q and another scattered electron carrying momentum k. So let's look at the corresponding operator. This 3 is actually your final state, and on the right hand side you get initial state. So initially there's electron carrying momentum k, which gets annihilated here in the first electron-phonon interaction vortex, and there is absorption of phonons carrying momentum minus q here, so that the intermediate state will be electron stay with momentum k prime, so that this momentum conservation is satisfied, which is k minus q is actually k prime. So now that electron carrying momentum k prime is further suppressed because this operator is actually connect with this c k prime operator, where this created electrons after the first interaction vortex will get annihilated again because of this destruction operator c k prime here. But then after electron-phonon coupling for the second time, it actually emits a phonon with momentum minus q, and also emit another electron carrying momentum k. Of course, this prefactor, this epsilon 0 minus 0 inverse, will be this coefficient or probability amplitude of such event. So this is the process where you absorb a phonon first and you emit another phonon later, but in the intermediate state is the pure single electron state. Another processes is this, which is very different processes. So the 3 operators on the right represent its initial state. Another 3 represents the final state. But you could interpret this second process in very similar fashion. So one electron carrying momentum k is annihilated, and then after the first electron phonon, it generates electron carrying k prime and also a phonon carry momentum q. So again, momentum conservation tells us that k is actually k prime plus q. Good. So these two terms have the same definition of the q, which is k minus k prime. Of course, it is satisfied here. And intermediate state consists of 2 particles, one electron carrying k prime, another is phonon carrying momentum q, and then these 2 particles get merged into the single electron state carrying momentum k right here. So that this phonon, intermediate phonon state, is annihilated and it disappears from this final state. So in that second case, you absorb and emit a phonon intermediate state. Okay, so the phonon doesn't appear initial nor in the final state, but the first coupling involving absorption of a phonon in the beginning and emit another phonon in the final state. So let's look at this energy denominator here. So 1 over epsilon 0 minus h0 stands for the intermediate energy denominator, which is epsilon k as the electron kinetic energy plus h bar omega and minus epsilon k prime. So this epsilon 0 refers to the initial total energy, which is the single electron, free electron epsilon k, and free phonon energy h bar omega minus q here, right? So you sum over these 2 energies, you get epsilon 0, and h0 here refers to the h0 operator in the denominator acting on this intermediate state, which is nothing but electron kinetic energy in the intermediate state, which is epsilon k prime. So you subtract these 2 energies, you get this energy denominator when you really operators on the intermediate states. So likewise, you get the energy denominator for the second term, which is very similar but different. Again, this is the energy difference between the initial and the intermediate state. So H0 is the initial state total energy, which is nothing but a single electron carrying momentum k, which is epsilon k. What about this H0 in the denominator? Well, if you project this operator onto this intermediate state, you get two particles, right? So one is the electron momentum k prime and energy epsilon k prime. Another is free phonon h bar omega q. So you should add this two energy. You get H0 acting on this intermediate state. And the energy denominator is the difference between the initial energy and the total energy of an intermediate state, which is this. So you can see that the energy denominator is very similar but slightly different because of the plus minus sign. Okay? It involves whether this phonon is absorbed and emitted in the initial state or in an intermediate state. And this intermediate state is called the virtual processes because this virtual processes only exist in the intermediate state and which will not appear either in the initial or in the final state. Okay? Which means that, as an observer, you don't really know what's going on, in the intermediate state, but you only know the initial and final state. So to really probe this virtual processes, you need a clever design of your experimental equipment. Otherwise, all you can see is the initial and final state, and you don't know, what's going on in the black box. So the virtual processes, the processes that arise in many quantum systems. So when you study quantum mechanics, you know very well that there are some virtual processes which is allowed by quantum mechanics, but you cannot observe or measure this intermediate states because it is not a measurable state. So for example, if you have a tunneling experiments by sending electron into this potential barrier, and then this electron actually tunnels through this barrier, but something must stay inside the barrier, but you don't know for sure because you have no way to probe the states inside the barrier because there's no physical observable that allows you to detect whether there's an electron inside the barrier. You know this paradox, right? When you studied quantum mechanics, you know that this Heisenberg uncertainty principle forbids you to really observe such a virtual state. And this virtual process is precisely the combination of the virtual state where you don't know whether this virtual state exists, but you know the consequence of that. So let's stop here right now, and next week we will continue studying the consequence of electron-phonon coupling on both the phonon frequency and also on the electron dispersion or the electron band. Okay, so please read the corresponding chapters in our reference books and think about this physics and make sure that you understand and do your homework. Okay, I'll see you on Monday.